the quadratic formula. Let me just write that down. This is not the way we're going to do it, but one way to do this would be the very cumbersome negative b, which is minus 26, plus or minus the square root of b squared, and I'll just write this down, 26 squared minus 4ac. This is your a, this is your c. Well known, very well known result. 4 times 1025. You know that dot connotes multiplication. So 1025 and dot 169. All right, all over. It's 169. Let me extend the radical there. Then also 2a. This is all over 2 times this, which is 2050, right? Now again, this is not why I did this video, but this would be a way to do it. Then you'd have to deal with these large calculations. In other words, 26 squared is pretty easy to figure, but then you have to do 4 times 1025 times 169. That would be 4ac, right? So let's look at another approach here that's actually easier computationally. What we do is realize that if you subtract 1024 from both sides, you get a perfect square binomial on the left-hand side. That's the trick here. This 1025 all of a sudden melts in your mouth when you subtract 1024 from both sides, which is this first line. Okay. The second line is recognizing that the trinomial is a perfect square binomial. X plus 1320 squared is equal to x squared plus 2 times 13x plus 13 squared, which is the line, which is this line right here. Okay. Why did we do that? Well, we can take the plus or minus square roots. All right. And this is all standard stuff at this point without any large calculations. Now, the thing to recognize right here, the one big calculation you have to do, I guess if you want to call it that, is to recognize that 2 to the 10th, 2 raised to the 10th power is equal to 1024. That's not too hard to do in your head, actually, knowing that 2 to the 8th is 256, 2 times 256 is 512, and 2 times 512 is 1024. So we get this, all right? But by laws of exponents, when you take the square root, you get 2 to the 5th, which is what you see right here. Okay, 2 to the 5th is 32. Okay, now y'all notice what we're doing here. I kind of like this notation here. This is the standard plus over minus, but when you subtract it from the other side, okay, you actually get minus over plus, which is important. It's just a way to write it. I think it's important to keep track of that. The plus over minus becomes the minus over plus when you subtract these two objects from the other side, okay? Now, the big step right here is knowing that we can factor the x out, okay? You have an x common to both of these terms right here. And so we get this statement and everything's happy because we have a coefficient of x that's a pure complex number, or I mean a complex number. So we get x is equal to this, and we're done in a certain sense, but let's go ahead and write it in what they call standard complex form. Notice that we can multiply top and bottom. This is kind of a standard trick. Let me envelop this in parentheses. We can multiply by 1 plus or minus. This is the standard conjugate trick that's based, it works because of the difference of two squares formula. Okay, but we're going to multiply by a cleverly disguised version of 1. All right. Okay, and then 1 plus or minus 32i. Okay. And this is standard. I mean, this is standard idea here. It's how you divide two complex numbers. Now, if you go through the arithmetic on this, let's see. You would get x is equal to minus 13, okay, plus over minus, I guess we should write it, plus over minus 416i. That would be in the numerator. Now, the reason why we're getting some mileage out of this, let me get some more space here. Okay, we actually get 1025 in the denominator. Now, you may be asking, well, how did you get that? Well, notice that the reason why this number comes out just to be an integer, a pure real number, is that if you have this form a plus bi, where I is the imaginary unit, I is defined to be is the square root of -1, I squared is equal to -1. But if you have a plus bi, I wrote that like a subscript, I didn't mean to do that. But if you have a plus bi times a minus bi, and y'all, again, this should be a big I here. Let me, just to avoid any ambiguity here, let me erase that. Eraser on that. Okay, so this is I, bi. Y'all, and again, I squared is equal to -1. And that's what defines it, or you can think of it as I is the same thing as the square root of -1. Now notice when you square this, you get the bi, the bi's cancel, the ab, the minus this term, these two terms right here cancel with each other, and so you end up with a squared plus b squared. Okay. Again, many of you probably don't need to see this, but that's because no matter what happens here, you're going to have the minus sign canceling here. The minus sign canceling with I squared to give you plus b squared, which is exactly what this is. This is equal to 1 plus 32 squared. Okay, so that was your so-called big calculation. But to me, it's kind of nice that you can do a problem like this in this fashion. You might be saying, well, I just soon use the quadratic formula right here, like we did at the very beginning. But it is kind of pleasant to know you have that as an objective or as a possibility, you know, rather than just doing this banal calculation right here. Again, this would be sort of involve this calculation 4 times 1,025 times 169. But in any event, we've solved the problem. And I will say these things are designed to work, right? This part of it right here, combined with x squared, is a perfect square trinomial. If you didn't have a perfect square trinomial that you could create by doing this first line manipulation, it would, you know, you'd probably just have to do the usual routine, complete the square, quadratic formula, check, see if it factors. But anyway, that solves the problem. Let's see, where do we write the answers here? Yeah, this part right here is the answer. All right, good night.